Welcome Engineering Statics. This is ENGR ampersand 214 in the Washington State Community College system. In this very small mini lecture, we will be discussing vector magnitude and unit vectors. So, vectors are used to describe some of the most important quantities that we work with in engineering statics, and things like moment or torque, and of course force, and things like position relative to a reference point. So the two important components besides the units, because there's three important components of vectors, are the magnitude of the vector, which will include a unit, pounds, foot-pounds, newton-meters, meters, and its direction. And one of the most, maybe the more complicated parts of vectors is their direction. So one handy thing that we will frequently do in engineering statics is separate out those two aspects of a vector quantity. So we need to have bomb-proof ways of expressing a vector in terms of both its magnitude and its direction. So say we have a force vector, and it's pointing from the origin to somewhere out in space. So we might want to be able to describe how many newtons is it pushing with, and what direction is it pushing, and what would happen out here where it's maybe contacting some body if instead of pushing with 10 newtons I pushed with 20. But I want to push in the same direction. So can you describe a direction, and then I can maybe decide how hard I want to push later? That's a really useful thing to be able to do. So we're going to look at separating out a vector's magnitude and its direction when we have a vector that's described in terms of the x, y, and z coordinate axes, or its x, y, and z components. So maybe we need to take a little step and define components of a vector. So one way we can envision a vector's components is to look at the vertical projections of our force vector arrow. Let's imagine that this arrow representing our however many Newton force acting on this body. Let's use the length of this arrow drawn on our schematic to represent the magnitude. So we can look at the portion of that vector that is parallel to the x-axis. So that's the x component. The portion parallel to the y-axis, which is the y component, and the portion that is parallel to the z-axis, which is the z component. And that's what our subscripts are: f sub x, f sub y, and f sub z. Now if you remember your tip to tail vector addition, it's not hard to see that if we were to somehow designate each of these three component vectors with something that denotes their direction, they would add up to the full vector f. So one definition of vector components is that all the components add up to the original vector. That's one way a vector's components can be described, as any collection of other vectors that add up to the original one. They also need to meet a rule that we'll derive here, which is that they will follow the Pythagorean theorem, and in their magnitudes that they will add up as the square root of the sum of the squares. So we're also at this point going to define a unit vector. A unit vector is a vector with direction only. In other words, it has unit length. It also has no actual units. It's dimensionless, kind of like radian, degrees, and other dimensionless constants we use. Now it can be in any direction. And in fact, we use unit vectors to define direction. with no magnitude. Then we can go zinging whatever magnitude of force, torque, displacement, whatever the heck we want down it. It defines direction only. And the symbol we use to denote a unit vector in a given direction is a little caret hat. So F with a little caret hat means in the direction that this vector F here is pointing, but no magnitude, and no units, no newtons, unit vector, just one. There are three really special unit vectors that we really like, and they are the ones that define the coordinate axes. So we have an I hat, and a j hat, and a k hat. Those are special numbers. I hat, j hat, and k hat are, by definition, the unit vectors that define the coordinate axes. Well, I can multiply this length, or this magnitude, because we're really talking about magnitude of a force, f sub x, I can multiply it by unit vector I, which has no length and no dimensions, but it'll tell me that this is pointing in the x direction only. Same thing with f sub y and f sub z. Now I can add those components and get my full vector. So my full force vector F is the magnitude of its component that's pointing in the x direction times unit vector I hat that denotes the x direction, and likewise for y and z components in the j hat and k hat. These unit vectors give me a direction, and they turn what otherwise would have been a magnitude into an actual component vector. Now let's look at, now we've defined a unit vector. We've shown how handy it is to have unit vectors that represent the coordinate axes. Now let's take a look at length here. Let's find some right triangles. We have a right triangle here, and we're going to define this sort of temporary vector here. We'll call it A. Okay? So we know that the length of vector A by 2D Pythagorean is the square root of f sub x squared plus f sub y squared. Now notice I don't have any vector designations, so I'm only talking magnitude here because I don't have a vector notation. So if I wanted to add A, the length of A, to the length f sub z, I know that I should, because I have another right triangle here, I should get the length f. I should be able to say that the length of f, or the magnitude of f, is going to be the square root of a squared plus f sub z squared. Well, what's the length of a squared? Well, it should just be f sub x squared plus f sub y squared. Basically I have two right triangles. So the magnitude of a 3D vector, we basically have kind of an extension of our familiar Pythagorean theorem, is just the magnitude of each of its components in the coordinate directions squared, take the square root. This is vector magnitude. So, anytime that I want to turn a whole vector into a unit vector, which is a lot of the time, then I just have its pure direction and I can assign another magnitude. All I have to do is take the original vector, just cross that out, grabbing the eraser here on the whiteboard. This is akin to using your elbow to erase something on a classroom whiteboard. And I am going to divide by that length, by that magnitude. So there'll be a lot of times that you have an actual length type direction that you'll get from two physical points separated by meters or feet. And you'll be told, hey, your direction of interest is in a line defined by 2 points, or in some kind of, some compass direction that you'll define in feet. You can create a position or a radius vector using those 2 points that will have a length in feet or meters or something. But then you're going to want to get rid of that actual length if you want to send a force or a moment or something else down its direction. You have to turn it into a unit vector. And then you can assign any magnitude, even a magnitude with different units, because a unit vector has no units. You took away all the meters along with all the length of meters. So this is unit vector f here that corresponds to this full vector f. So you Pythagorean, 3D Pythagorean or 2D or whatever, it's all the same because one of these might be 0, that's okay. To get the magnitude, divide each of the components by this magnitude. Which brings up another awesome property of vectors that we may or may not have defined. And that is scalar multiplication. One of the reasons that we can do this so easily is, of course, we can multiply, like say we have a scalar alpha, 5 feet. We can multiply that by a vector A, and that will multiply across all of the components of A. So scalar multiplication is distributive over vectors. Likewise, if we could multiply we could have a scalar multiplying a vector sum, and you can distribute that, and so it would be like A times alpha b. So that is a property that we are effectively leveraging, because this big square root term is going to end up going to divide each of these different terms. That's why we can put the big long quotient bar on our fraction here. So in creating a unit vector from a vector's magnitude in its full expression, we are leveraging the scalar distributive property, multiplication property with vectors. So I would strongly recommend that in your textbook there will be, I'm sure, a section on commutative, distributive, associative properties of vectors and scalars multiplying and dividing. That will help you quite a bit. I may or may not have caught them all explicitly in my lectures. I will have leveraged them, possibly without calling them out explicitly, so I would highly recommend that you go back and you search them out. There will be times when we leverage a few of those properties explicitly to do proofs of some super handy properties like principle of moments, and so we'll go over them again. But it never hurts to take a look at them, and if I have done a step that confuses you, how could you do that? Please reference the properties of multiplication and addition of vectors and scalars, and that is very likely where one of them would have come out. Tried to point these out as I went, but again, if you saw something that you didn't know how I did it, I was leveraging one of those properties. So that will help you as you continue, but this is the main review for unit vectors, vector magnitude. We'll see you for another video.